today we are going to start the lecture on advanced reaction engineering. So, today we will discuss about the space time, space velocity and CSTR reactors if it is in series and parallel. So, that we will discuss. In our previous class we have discussed various reactors in different way or that we can connect and how that would be affect in overall volumes of the systems that we have discussed. Now, today we will discuss about the space time and space velocity, and then we will discuss the single CSTRs for the first order reaction, second order reaction and CSTR in series and then CSTR in parallel. So, what would be the effect in overall volumes conversions that we will discuss, or how we can connect a number of CSTR reactors in series to get a specified conversion. So, have to means how we can find out. So, how many CSTR we should connect in series. So, in our previous class we have discussed that if we connect a number of means instead of using a one CSTRs, if we use more than one CSTRs in series, then there's the total volume requirement would be less compared to the single reactor. Means there is, if we use multiple CSTR in series instead of a single CSTR, equal amount or equal volume of the larger volume of the CSTR. So, then in case of the two CSTR connected in series, there's we get there is some advantages, means in terms of volume or conversions. So, okay, so that we will discuss more details. So, now we are going to discuss about the space time and space velocity. So, what is called space time? So, that is the time necessary to process one reactor volumes of fluid based on the entrance conditions. So, it is dividing the reactor volumes by the volumetric flow rate of the entering of the reactor. So, here we have studied that, let us say this is a CSTR reactors, let us say this is. So, here its reactors has a particular volume, here the reactant that would be fed inside of the reactor for that reactions. So, here this is the volumetric flow rate, this is the volume of the reactor. So, if we volume it has units dmq and here volumetric flow rate it has units dmq per second. So, the space time that is expressed in terms of tau. So, that is equals to V by V naught. So, V by V naught, that is the space time. So, dmq it is expressed in terms of time. So, space time, that is actually the holding time or mean resident times for that particular reacting mixtures or that reactant, that is or reactant component that is passing through that reactors for that when they are entering and taking part in the reactions. So, with the help of that reactor volumes and volumetric flow rate, we can find out or we can say the space times for that particular reactant is that particular value, means in terms of a second, that may be 10 second, 30 second, 20 second, 1 hour, 2 hours, that may be the space times for that particular system. The space times not only depends on the reactors, it also depends also on the reactions also, reaction to reaction the space times will vary. Okay, so, here I am showing the typical space time value for various industrial reactors. So, depending upon their production capacity. So, let us say batch reactors, suppose we have a batch reactor CSTR or plug flow reactor. In case of the batch reactor, it has been observed that the mean residence times is within range of 15 minutes to 20 hours for a particular reactions to complete it. Let us say the production capacity is 1 into 10 to the power 5 ton per year. In case of the CSTR reactors, if you use instead of a batch reactor, if you use a CSTR reactors, so then there the time mean residence time 10 minute to 4 hour that are observed. So, in case of the production rate also here is higher. Similarly, if we use a plug flow reactor, so here the residence time or means residence time is 0.5 hour to 1 hour, and here the higher production rate also we can get, a production capacity is higher compared to the other reactor. So, if we change one reactor to another reactor, the space times also would vary from reactor to reactor. So, depending upon that we can get higher production, means for if a particular reactions, if you need higher production rate. So, then that way we can change from one reactor to another reactor, by that way we can change our production capacity for a particular reactions. So, here you can see that space time for a particular reactions. So, here we have taken ethane to ethylenes, means ODH reactions, oxidative dehydrogenation reactions. In that case, that reactions if we conduct in a plug flow reactor and at these temperatures, at these pressures, then the space time is 1 second. So, that reactant molecules that pass through that reactors, that residence time should be or space time should be 1 second. So, if it is more than that, then we will not get the desired product or conversion selectivity, that would affect overall rate, conversion, yield, selectivity, everything. So, therefore, this is the very important space time. Similarly, for catalytic reactions or catalytic cracking, if we use a packed bed reactor, in that case if we use high temperature 490 degree centigrade temperature, 20 atmospheric pressure, in that case it has been observed that the space times or residence time that should be 1 second to 400 second within that time. And for nitration reactions, ethanol to ethyl acetate reactions, if you use CSTR reactor, here it has been observed that ethanol to ethyl acetate production. So, if we use CSTR reactors, then the reactions we have to conduct for 2 hours, means the residence times of the reactant molecules inside of the reactor, that would be 2 hours. So, long period you can compare. So, reaction to reaction for this particular reaction space time is 1 second, here it is 2 hours, and for this particular reaction is 20 minutes. So, reactions to reactions, the residence of space times that would be different. So, space time is very important parameters whenever we go or design a particular reactor. Similarly, for space velocity also, it is actually the reciprocal or inverse of space time. So, tau is the space time. So, inverse of the space time, that is the space velocity. So, v naught by v, that is the unit is second inverse, that is the space velocity. Means if we fixed any time frame, so let us say 1 hours or 30 minutes, to 1 day. So, within that period of time, so how many number of reactor volumes of feed that we can treat for that particular reactions within that particular reactor. So, that we can actually indicate, means let us say there is reactions for a particular reactors we are using, space time is low, very high value, phase time is very low value. It signifies the means, or we can from that value of the space value we can conclude that whether the reaction is very fast, reaction is very slow, or what would be the production rates, that we can indicate or we can get an idea. So, here that we will discuss more details more later. So, here the space velocity we can express in terms of, we said that any reactions that may be either gas phase reactions or maybe it is a liquid phase reactions. If it is liquid phase reactions, so liquid our space velocity, that space velocity, but that is in term for liquids. So, we can write liquid flow rate, and if you know the volume of that particular reactor, so that way we can liquid our space velocity we can find out. And in case of the gas our space velocity for gas phase reactions, if we know the volumetric flow rate of that particular gas or reactant component feeding inside of the reactor at a particular rate, and if we know the volume of the reactor, so then gas hour space velocity we can easily find out for this particular system. Okay. So, now we know what is called space times space velocity. Now, we are coming for the reactor designs, how that we can use, or that are means whenever the design equation or equations will come. So, everywhere we can express in terms of space time also. So, here we have taken a CSTR reactor. So, here you can see here reactant is entering, this is the CSTR reactor. So, here the concentration, initial concentration of the reactant component A that is feeding or entering into the reactor is Ca naught, and V naught is the volumetric flow rates of that reactant entering. V is the volume of the reactor and this is the stirrer, and tau is the space time, that is V by V naught. Okay. So, here X is the conversion, C is the outlet or exit concentration of the reactants, or that is the product coming out from here. So, here the design equation we have already derived. So, this is the design equation for a CST reactor, F V equals to F A naught minus F A by minus R A. So, here this F A naught, F equals to F A naught minus F A naught into X, if we substitute here. So, then these equations we can write V equals to F A naught into X by minus R A, F A naught we can write C A naught into V naught. So, that we can substitute here. So, then the equations of design equation we can express in terms of C naught V naught x by minus R A. Okay. So, then here V is there, here V naught is there. So, we can divided both side by V naught. So, then we can get V by V naught equals to C naught x by minus R A. So, here this equals to tau equals to C naught x by minus R A. So, this is the space time expressing in terms of initial concentration of component A, conversions for that particular reactions, and minus R A, that is the rate of the reactions. So, space times we can expressing this way. Okay. So, now here the reactions we make means conduct any reactions, first order reactions, maybe a second order reactions. So, minus R A we can write K into C A, that is for first order reactions, minus R A equals to K into C A whole square, that is the second order reaction. The rate we can write this way. Okay. So, now let us say the reaction is first order, n equals to 1, that is the first order reaction. So, rate equals to minus R equals to K into C A, or C equals to we can write this way, or C A naught equals to this way also we can write. So, this is the space time and concentration rate conversions, how they are related, just we have derived here. This in these equations, these rates, if it is the first order reactions, then we can substitute this. Okay. So, if it is the first order reactions, this minus R A we can substitute here, then we can express this in terms of concentration, then C A naught minus C A, that is equals to C A naught into x, this part we can substitute here. Okay. So, then after rearranging these equations, this tau equals to this. So, here if we rearrange the equations, so we will get this left hand side, that is the concentration, final concentration of the reactants here, this is, and this is the initial concentration. So, final concentration after egg outlet or the exit of the reactors, the concentration of component A, that would be C equals to C A naught by 1 plus tau K. Okay. So, or we can write this in terms of these also conversions also, since here you can substitute this in terms of this. So, then it also we can write this way. Okay. So, after rearranging either this way or this way you can write, means x equals to tau k by 1 plus tau k, this way we can write, means space times and conversions how they are related, or if we know the final concentrations, C A naught is the known, tau k value is means for a particular reactions, K into C A, that is the reaction rate constant. So, reaction rate constant small k, that is known or specified for a particular temperature, that we can put space time if it is known, space time I said V by V naught. So, volume of the reactor we know, volumetric flow rate we know. So, space time we know, initial concentration known. So, then final concentrations, what would be the concentration at the end of the reactor, that we can find out. So, if tau and k value is known, that we can put here also, even the conversion, what will be the conversion, that also we can find out. So, final concentration conversions, anything we can means find out using these equations once we know the space times and reaction rate constant value. So, here is the equation, design equation for the CSTR reactor for first order reactions. We have expressed the conversions in terms of tau k by 1 plus tau k. So, here tau k is we can express also, or we can simplify, that is the dA. dA is called Damköhler number for first order reactions. So, these equations we can write this way. So, x equals to dA by 1 plus dA, or tau k by 1 plus tau k we can write. So, what is actually significance of dA value? So, dA actually, let us say for a reactions we have this, and for a reactors we have volume V, volumetric flow rate we know. So, then quick estimate means these are the parameters we have, K, volumes and volumetric flow rate. So, then what would be the conversions we can estimate. So, here tau k value by 1 plus tau k. So, tau value we can easily find out, volume by volumetric flow rate, and reaction rate constant is given. So, these are the value if it is known. So, we can put, we can say that whether the reactions the conversions means this tau k dA value we can and gets. Okay. So, dA value means Damköhler numbers. If it is, let us say its value of dA is 0.1, so then it indicate very small value, then the conversion is very low. Okay. If dA value is 10 or more than that, then 90% conversion is possible. So, first if you are able to calculate the dA for this particular reactions, so dA value is very small value, that is d equals to 0.1 I said, then conversion is very low, and if dA value is very high, then we can say that high conversion chances is there. So, here if we maintain that particular operation conditions for that particular reaction in that particular reactor, so then we can get high conversion. So, it quickly we can estimate. So, either depending upon that dA value. So, similarly for second order reactions also, when n equals to 2 second order reactions, so we can write the rate equals to this, and we can put in these equations in the CSTR design equations in terms of tau, conversion, initial concentrations. So, here if we put this value and if we simplify or rearranging similarly as we did for first order reactions, so then conversions and Damköhler numbers we can write it this way. Here the Damköhler number for second order reactions is tau k Ca naught. So, tau is the space time, Ca naught is the initial concentrations, and k is the reaction rate constant. So, these are the from the beginnings we know before start any reactions in a particular reactor. So, then conversions, what would be the conversions by changing tau value, k value, concentration value. So, we can easily estimate or we can calculate. Okay. So, now how that would be useful means here this, let us say now if we are going to design a CSTR reactors, in our earlier cases we have discussed that let us say we have a reactors number of reactors 2, 10, 20 reactors CSTRs we have. Instead of smaller CSTR in series we will use, or instead of that equivalent amount of large CSTR reactors we use. So, in that case we have discussed that. So, if we use smaller number of CSTR reactors in series, that is much more advantageous with respect to the larger volumes CSTR reactors. So, therefore, here we will show that how, suppose we want to get a 90% conversions for a particular reactions, then how many CSTRs we have to connect. Means one larger CSTR will not use, instead of that we will use a series of CSTR reactors in connected in series, this way we will connect. So, here this number means how many numbers 2, 3, 4, 5, 10, 20, how many number of CSTR we should connect in series. So, that also we can predict to get a desired conversions. Conversion is fixed for a particular reaction data, laboratory data we have. So, all data we have, conversion if you are fixed at 90% conversions we need. So, then how many CSTRs we have to connect in series. So, here that we can get it. Here reactant, let us say initial concentration C naught, V naught that we have used for reactant for reactor 1, and here reactor 2, two reactors we have connected in series. Here partially converted product reactants, that is here some conversions should be there. Here particular rate is there, volume is there for this particular reactors. Here conversion after this reactors, when reactant is passing, the conversion is XA1. Here the concentration of the reactant that is leaves from that particular reactor, reactor 1, that is Ca1, and when that enter again into the second reactor, here rate of reaction is minus Ra2. Here the volume is V2 of this particular reactor. So, here after conversions that final conversions will get X2 and concentration is Ca2. So, here is two reactors will connected in series, we develop some equations means design equations. So, when 1, 2, 3, 4, 5, 6 reactors will be connected in series. So, then what would be the conversions as per our requirement of conversions. So, then how many reactors we should connect in the series. So, that if you want to get that answer. So, then for reactor 1 the design equations is this Ca1, that is the final concentration that is coming out from the reactor 1, and this is the initial concentrations, and 1 plus tau 1 K1. Tau 1, what is tau 1? Tau 1 is the first reactor's space time, tau equals to V1 by K1 small k volumetric flow rate. So, tau 1 equals to V1 by V naught. So, here first reactor is volume V1, V naught is the reactant flow rate. So, tau 1 we know, Q1 for the rate constant for this particular reactions. So, then Ca1 we know, And for the second reactors, this is the design equation for second reactor. So, we can express in terms of concentrations also. We said Fa equals to Ca naught into V naught. Similarly, Fa equals to Fa1 equals to Ca1 into V naught. This way we can write. So, then we can write the volume for the second reactors or design equations in terms of volume and concentrations we can write this way. So, here tau 2 is V2 by V naught. So, here V2 is the volume of the second reactor. So, now in these equations, here's after rearranging these equations, if we rearrange in terms of concentrations, so then the equations would come this. Here this equation, here Ca1 and Ca2 is there. So, Ca2 we are putting in the left hand side, that is the final concentration that would leave from the reactors. Here C1 we have derived, now Ca2 we are deriving, Ca2 is this. Okay. So, Ca2 in terms of Ca1, so these Ca1s will substitute here in terms of Ca naught, Ca naught is coming this and 1 by tau 1 K1 replacing here. So, here's tau 1 is V1 by V naught, tau 2 is V2 by V naught. So, if here V1 and V2 both are may be same or may not be same, means the same equal size CSTR we may put in series, or this is unequal CSTRs, here V1, here V2, volume are different. If equal size CSTRs we are connected in series, equal size means both the reactors, here V, here also V, both the reactors have same volume, size of reactors means this 10 liter, this is also 10 liter, this is equal size CSTR, here 5 liters, this is 10 liters. So, this is unequal size of CSTR in series. So, here's whatever we have derived the concentrations, that is based on if tau 1 and tau 2 both are different, means if V1 and V2 are different, then tau 1 and tau 2 would be different. So, like that n number of CSTR that may be equal or unequal size CSTRs we can put in series. So, that way if both the reactors are equal, then tau 1 tau 2 would be the same, and reaction, since the reaction is the same reaction. So, reaction rate constant would be the same for the same reactions we are conducting in the series in the all or both the reactors. So, therefore, Ca2 equals to Ca naught by 1 plus tau k square. Here this tau 1, if V1 equals to V2, V1 equals to V2, so then tau 1 equals to tau 2 we can write, and for the same reaction K1 equals to K2 equals to small k we can write. Okay. So, therefore, this equation simplify, and the final concentration, this is initial concentration, that is feeding concentration of that component A. So, this way you can write. So, here's if similarly equal size CSTR, if we connect n number of series, here 2 reactors we have connected in series, therefore, the final concentration is coming this way. If a number of CSTR we connect in series and all reactors are equal size, so then final concentration from the nth reactors, here the concentration we get Can. If this is Ca naught and this is n number of reactor connected in series, the final concentrations from this exit inside in between whatever the reactors are there, so we do not need to find out the concentration, just we need the final concentration of the reactors. So, then we can find out what would be the exit concentration of the final reactors. So, then if we n equals to maybe 10, n equals to maybe 20, n equals to maybe 5, any numbers that may be. So, we can substitute here and initial concentration tau and k value we can put. So, then we can find out final concentration what would be. So, here this is expressing in terms of Damköhler number also we can expressing this. We note Ca equals to Ca naught, Can equals to Ca naught into 1 minus x, or this is the concentrations, final concentration of any reactant A, this is initial concentration if conversion is this. Similarly, for nth number of reactors also we can write this Can equals to the final concentration Ca naught minus 1 minus x, and here this Ca naught and this Ca naught we are substituting this. So, then this part is coming here and this part is coming right hand side. Okay. So, this is equals to Can, we can write this. Now, we are rearranging this. After rearranging we are getting in terms of conversions, conversions equals to 1 minus 1 by 1 plus dA to the power n. So, or we can write this x equals to 1 minus 1 by 1 plus tau k. Here the design equations means final concentrations we know for nth number of reactor, either this or this, anyway we can write, and conversions also we can calculate, concentration also can calculate. So, now this is the red equations. In the red equation, minus R equals to k into C to the Can. Can is the final reactors, that reactants leaving, that we can find out, and that we can put it here. So, here this we are putting here from the these equations we are getting. Okay. So, these things we are getting, we are putting here, then red equations is this. Okay. So, here conversions, if we want to know, using this equation we can find out. If you want to rate of that reactions, if nth number of reactor is there, so then by putting n equal to 5, 10, 20 initial concentration, tau and k value, so then rate, corresponding rate we can find out. So, let us say here the effect of tau k or Damköhler number with the number of tanks in series. Let us say here tau and k value for a particular reactions. Here in the x, in these plots you can see here x axis we are plotting n number of tanks in series. Tanks in series means n number of CSTR in series. Okay. 1, 2, 3, 4, 5 like that, 20 reactors we are connected in series, that may be any numbers. We are placing number of tanks here, n equals to, we can put 1, 2, 3 like that. So, corresponding conversions from these equations, okay. So, here dA value we can change, dA value if we put Damköhler number, that is equals to 1 or Damköhler number 0.5, Damköhler number 0.1, that depends on dA value, depends on tau k. Okay. So, tau k is the constant value, but here tau is the volume by volumetric flow rate. So, volume if we vary, then tau value would change, dA value would change. Okay. So, then conversion, if dA value is 1, then the conversions and number of tanks would be follow this line. If dA value is this, then from the equations we can get the conversions. If number of tanks will increase 1 to 20, the conversions will vary like this, and when dA value or Damköhler number is very small value, 0.1 value, then the conversions lines will follow like this. So, here if we draw a lines, vertical lines, see the dotted line indicate that here's conversion is very high, here conversion is very low, here also low value conversions, this is x conversions, x y axis, that is the conversion. So, here if Damköhler number is 1, then 7 tank or 7 CSTR reactors in series if we use, then we can get high conversions. Okay. So, means we do not have to, which means to achieve, let us say 80% conversion you want to achieve, then 7 reactors we have to use in series, then we can get 80% conversions. We do not have to use 20 number of reactors or 10 number or 12 number of reactors. So, exact number of reactors easily we can find out, and that can say that when we are going to conduct a reactions, we want to design a reactor. So, then total 7 reactors if we connect in series, then we will get the our desired conversion, that is the 80%. If tau k value or dA value is very small 0.1 value, so then if we use tau equals to this, then we will get less than 50% conversions, close to 40 or 40% conversions that we are getting for that same systems or arrangement. Therefore, tau k value we have to increase, means how tau k value we can increase. So, tau k equals to or dA value we have to increase V by V naught into k. K we cannot change, volume, either volume we can change, volume we can increase. If we increase the volume, then dA value will increase. If V naught value decrease, then dA value will increase. Okay. So, dA value directly proportional to the volume of the reactor we can change, or dA inversely proportional to the V naught. So, either this way we can control that reactant feed stream. Here the volumetric flow rates we can change, we can increase or decrease, by that way we can change the Damköhler numbers, and by that way we can design the reactors, means whether how many reactors we need to get a desired conversions. Okay. So, similarly, if a number of CSTR reactors we placed in parallels, here earlier one was the series, here this is the feed is divided into n number of reactors, here 3 reactor was taken and that connected in parallels. Okay. So, here that same quantity of feed is entering in each reactors. So, volume is also fixed for each reactors. So, therefore, rate of reactions also each reactor should be the same. So, if we connect n number of reactors in parallel CSTRs, so then also we will get desired conversion is x1s. If we connect one reactors in parallels and n number of reactants CSTR reactors in parallels, in both the cases we will get same conversions, but overall total productions yield or production capacity that we can increase, but the total conversions we can get the same, we cannot change. So, here as per this type of model, so the total conversions we can say reactor 1 this, reactor 2 this, reactor 3 this, all would be the same similar amount of same volumetric flow rate, molar flow rates both are same for these reactions, that is reactant entering inside of the reactor. So, therefore, rate also would be the same. Okay. So, then individual reactors, that if Fa naught is the individual means reactor molar feed rate and Vi is the volume, X is the conversion, this is the minus RAI, that is the rate of that particular reactions. This is the design equations, okay, for a reactor. So, if consider reactor 1 I equals to 1. So, then if we can put, then total volumes V 1 equals to Fa naught 1 X by minus RA 1. So, that corresponds to the corresponding reactor. So, n number reactors we are connected in parallel. So, there we can write this way. So, volume of the individual reactors, then we can total volume was V, total number of reactors n. So, then Vi is the individual reactor volume and total molar flow rate Fa naught I equals to Fa naught by n. So, we can substitute this here in this design equations. So, then we will get this here at the ends we will get V by V equals to Fa naught by X by minus RA. So, here you can see the total volume that is equals to V and Fa naught is the total molar flow rates. So, here you can see that the conversions achieved in this case in any one of the reactor is the same or identicals, where the conversion identical conversion with the reactor having equivalent large volumes of the reactors, means instead of parallel or series whatever, the if the same amount of means reactor number of reactors if we connect in parallel. So, then there is no actually advantage using CST reactors in parallel except high productions only that we can get, but otherwise in terms of conversions we will get the similar or same amount of conversions. Okay. So, today is up to this. Thank you.